Hello everyone and welcome to the first session as part of the EN workshop, which is about the power system principles for non-electrical engineers. Could you please confirm you can hear me okay and you have got the webinar slide visible? Excellent. So what I'm going to do tonight, actually my time of course, is basically give you a general concept of the power systems, with a special focus on the switching devices for the transformers and the protection systems and the power quality. All right. I'm not going to be too fast, and at the same time I'm not going to be too slow because I've got a lot of slides actually to cover. So the first thing is, okay, so this course is about electricity. I know that there are some people like electrical engineers among you, but my assumption is that I'm just going to assume that whatever your knowledge and background is, it is not mainly focused on the power engineering, say at an engineering level. So I'm just starting from a very, very basic question saying, what is electricity in effect? We have got a lot of electrical appliances all around us, like TV, like the hair dryers, like the electric bulb, like the washing machine, like the iron or something, all right? So what is electricity? We need electricity to run all these devices. Electricity has got a number of different important parameters by itself. One of them is the electric current. Who in this class can tell me quickly other parameters, important parameters that you can find within electricity? Could you type please, what are other important parameters that you understand? Maria, perfect. Voltage is another one. So we have got current and voltage, and I can still find other parameters. Okay, amperage, Alec, is the same as current, okay? Amperage is the same as current. So voltage and current and, yes, power factor and what is the combination of current and voltage? What is the multiplication of voltage and current? Resistance is okay. So Paul, what is the unit of measurement? All right. So the parameter itself is power. Is that right? Excellent. So we have got power, we have got voltage, we have got current, we have got resistance. There is something more. What is the thing in your, okay, so if I ask you what is power, you would say power is the thing that does the job. Okay, for example, you have got lights, you have got the motion, you have got the machine running or something like that, you have got the TV on, you have got the radio on, so this is power, okay? So if I ask you, what is power during a period of time? What is the thing that your electricity bill is based on? Every month you are not paying for power, you are paying for something else. Your electric bill is not based, I'm talking about residential, okay? It's not based on power. It is based on, okay, that kilowatt hour is the unit of measurement for, that kilowatt hour you are referring to is the unit of measurement for, starting with the letter E, my dear friends, it is not electricity, nope. It is energy, okay? So the issue is the electric or electrical energy, E, all right? So we have got power, we have got energy, voltage, current, and resistor and power factor. Okay, question for the class is this. If I'm just going to, so don't worry about I'm not turning over the pages or something like that. I will do it quickly. But all I want from you guys in here is just to come into a very proactive contribution into the class activities so that I make sure that we are on the same page. All right, so we have got the same understanding about the electricity. If I want you to make a comparison, okay, between an electric circuit, okay, and the hydraulic circuit, so that you have got, for example, water, okay, in there. So let's say you have got a tank of water that has been installed at a height of h. Okay, so you have got that tank installed at a height, okay, and you have got water installed in it. That tank by itself has got a valve. So if you like, you can drain water out of the tank. All right. My question is this. If you want to compare this electric current with another feature of that hydraulic system, okay, of that system, that water or something like that, this electric current is similar to what? Electric circuit. Electric current in an electric circuit is similar to, Jeremy, the flow of water flow. Okay, so excellent. So that is similar to water flow. In your opinion, this electric voltage is similar to what in that system? You need something so that you have got a current, you have got a flow of water. So that has to do with that valve, isn't it? Is that right? Okay, so gravity is correct, amount of water is correct, but that, my dear friends, that gravity and amount of water together produce something so that as soon as you open the valve, the water will be running out of the valve, and the name is pressure. Alec, excellent. Okay, so we have got pressure as opposed to voltage. But either this system or that system, this pressure and voltage has got another name. Again, starting with the letter P. And who knows that? This pressure and voltage, another name that we can do, you can use for that in English is starting with PO. So, nope, it's not power. It's not power. So think about the dam. You have got power behind the dam. Yes, Hector and Maria, potential. Okay, so you need to have potential energy. Okay, potential energy is the thing that you, let's say, need to have for that. Okay, so basically, we have got the, let's say, the definition for current. We have got a definition for voltage. Now, in your opinion, this electric resistance that you are referring to, it is similar to what in that system? I give you one hint. In this electric circuit, tell me, what is the thing by which you can carry that flow of electric current? First, focus on the electric circuit. What is the thing that you have got to carry the electric circuit, the electric current from one place to another? Excellent. Conductor. Correct. That conductor could be line conductor, could be cable conductor. Okay, I'm asking, this cable or line conductor is similar to what in that system? In the other system. In here, you have got cables. Okay, so that's pipe. So once again, I'm asking, this electric resistance is similar to what? Anyone knows? It has to do with that pipe, okay? It has to do with that pipe and also that valve. Size, what do you mean by size? What exactly do you mean by size? Okay, so it goes back to the diameter, okay? The diameter of that pipe. So if the pipe is, for example, very wide, in that case, you can carry a lot of flow. Similarly, if you have got your wire, your cable, your conductor, very big size, in that case, you can have a lot of current in that conductor or pipe. At the same time, you understand that when the current is very high, the voltage or potential or pressure is very low, right? When you make it thin, in that case, the pipe is now thin. The wire is thin, okay? So it can carry very low amounts of current or flow, but at the same time, the potential, the pressure, the force, the voltage is very high. That's how this electric system works. However, rather than water, in here we have got other particles. We have got electrons. We have got protons. So that's the movement of these electrons that we refer to as the current, or the flow of electrons, rather than having the water. So when I want to get a resemblance between the two systems, I can say that I've got a water tank. Same amount of water can be stored in the tank. However, I can put it at a height of 1 meter, or I can put it at a height of 10 meters. So what's the difference? The difference is the potential. The difference is the potential, the energy, pretty much similar to what you have got behind the dam. It depends how big, how tall is your dam. Therefore, this water container tank at a height of 1 meter can be similar to a battery you have got with 1 volt potential. The other one can be similar to a battery with a potential or voltage of 10 volts. So that's the meaning of electricity. That is where we're coming from. So as long as you do not have any path between these protons and electrons, there is no current. Therefore, it is similar to that valve. As long as you have not opened that valve, there is no flow of water. Once you open the valve, it can be fully open or it can be half open. So that is the first bit of resistance that we put in there. And then once it's in the pipe, again, depending on the size of the pipe, the diameter of the pipe, the thickness of the pipe, there could be other resistances, even friction, for example. Okay, so this is similar to an electric resistance that you can have in an electric circuit, or something like this. Okay, so that one is referring to that resistance that you have got. So finally, you have got a load. The purpose of everything is that you are causing this electric current to flow for a purpose. In this case, for example, the purpose is to light a lamp. For your case, in that water system, the purpose could be to fill in a tank, to wash something, anything, okay? So you need to have an end user. You need to have a load. So all in all, I'm talking about discharging electrons. So we have got a positive pole and we have got a negative pole at all the time. The issue is to make a way just for the discharge of electric current and energy. Sometimes it is desired. It is controlled. It is within our control. Sometimes it is not desired. Like this lightning. So lightning is not desired. It is absolutely out of our control, and this is not what we want. So that's a very quick and huge and massive release of energy. The exchange of electrons and protons between the two surfaces, which in this case is the surface of the ground and the clouds. However, the controlled ones are what we have got for batteries, what we have got for generators, what we have got for capacitor banks. So we have got the controlled ones and we have got the uncontrolled ones. So what is happening in lightning is that that's a massive, huge electrical discharge between the molecules of the cloud and the ground. but there are some circumstances in here. Not at all the time lightning occurs in all places and at all heights. No. It depends on the geographical situation. It depends on the distances of the clouds from the ground level. It depends on the formation and configuration of those electrical charges of electrons and protons in the cloud and on the surface of the ground. It's more like a magnet. If by chance, right at that time when you have got a lot of rain, heavy raining, just by chance, if, for example, in a spot, if you have got lots and lots and lots of electrons accumulated in one place for any reason, and right at that time, if you have got positive charges above it in the cloud, as long as this distance is too much, nothing's going to happen. You're going to have just rain. But the clouds are getting closer and closer and closer to the ground. All of a sudden, there is a spark. There is a big arc. There is the release of energy between the cloud and the earth. And this is what we call the lightning. My question for the class is, in your opinion, what is the reason for that spark? Why there is a spark like that? Why is that? So in other words, I rephrase it. Why is that at a particular distance this spark doesn't occur, but as soon as that distance becomes less than something, that spark occurs? So there is something in between those positive and negative charges. And what is it? What is between this positive and negative that prevents resistance? What do you mean resistance? I'm talking about this example. This is not electric circuitry. This is lightning. What kind of resistance? The resistance is correct. I'm asking Alec and others, what kind of resistance is there in between so that you and I are safely walking in the street? It's raining very hard or something, and we are still safe, unless we are very, very unlucky and right at that spot there is a lightning and we may be killed or something, right? So what kind of resistance is in between? So physically, do you agree between that positive and negative charges there is air, isn't it? It is not vacuum, of course, right? You have got air. So that air has got a feature so that it will prevent these electrical charges to meet each other and build up a current unless they are very, very, very close to each other. And that feature's name is, it has got a name. It has got a name. If you have noticed the battery, you have got a positive pole, you have got a negative pole. There is something in between. Think about your car. Think about your car. What do you have inside the battery? You have got a number of cells. What do you pour in the cells in your car? Water? Battery. Do you pour water? Distilled water, and there is something else. There is something else. Acid. Yes, there is acid. So do you know the name of that acid in English? Starting with the letter D. Anything like that that comes in between and can control the flow of current between positive and negative charges. So you need to have a controller in between. So God has given us by nature that controller. One of those controllers is air. The name is dielectric. Okay, so you need to have a dielectric in between so that that dielectric naturally will control the flow of current. Okay, that dielectric has got a feature, and that feature is called dielectric strength. Therefore, naturally we have got air. That air has got a dielectric strength. That's why you just walk freely, and we have got a lot of cables, we have got a lot of transmission lines or something. You just walk, you just drive, and you are safe. Nothing happens because you have got air. And that air has got dielectric strength, and that air prevents that live conductor to damage, to injure, to kill you. That's what it is. But if you get very, very close to bus bars, to live compartments, to transformer bushings, to, I don't know, panels or something, yes, you could be electrocuted because that dielectric strength is compromised. This is what is happening in here. Okay, so that's the meaning of electric discharge, that when it goes on out of the control, in that case you have got an unwanted spark or electric arc. But as I said, it is a parameter of many different things. Like it is a parameter of humidity. It is a parameter of the distance between the cloud and the air. It is the parameter of the kind of things that you have got on the surface of the ground that creates that kind of electric charges. If, for example, the electric charges in the cloud, they are positive at the bottom part, and the electric charges on the ground are also positive, it's more like the magnets. They are not attracting each other. As a result of that, there is no lightning strike. The bad thing is that one side you have got positive and the other side you have got negative, and things get out of control. So in here, again, you can see that even the temperature is another parameter. How much temperature do you have? Because condensation is also important. That's how rain is created in the cloud. However, sometimes this flow of charges are funny, like what you have got for a static charge. It's a dry day. You and I are wearing rubber shoes. We are walking on a carpet. We meet each other. We are going to greet each other. We just shake hands. And after that, poof, you may have experienced that so many times. Okay? Again, you are trying to touch the door handle. You are going to get out of the room. That door handle is metal. You just touch it and poof, again, another discharge happens in there. You just try to comb your hair. Again, you can see that your hair becomes like that. Even you can attract some small tiny particles like paper with that comb. So it means that it's more like it's been magnetized or something. It can attract tiny pieces. So again, in here you have got the static charges. Sometimes these static charges are not just funny, okay? So it just gives you a giggle or something. Sometimes, no, it can chill people. Like, for example, the static charges that can be accumulated on a metallic frame of a panel, of a cubicle, or whatever. You touch it innocently and boom, you are electrocuted. So we must be very careful. It is not something to ignore. We must be very, very careful of that. So these are examples of the static charges. Therefore, if someone asks what are the limitations of this static charge, we say in thunderstorm clouds, the static charges can build up to millions of volts, which is of course very dangerous. It cannot move and is limited to what? To only small distances. So one of the limitations is the distance between the cloud and the surface of the ground. Static charge can cause damage to electronic equipment. The static charge can also cause uncomfortable shocks. Especially if this kind of sparks are close to flammable gases, they can cause fire, big fire, like the pump stations or whatever. So we have got these things already in place. So as I said, We have got controlled and uncontrolled flow of current. The controlled ones, like we have got in batteries. So as you can see in here, we have got an electrolyte in between. That electrolyte in between, that can create, as I said, dielectric strength. And at the same time, it is responsible, as you can see in between, responsible for controlling of the flow of current, electrons, protons, so that you can keep this battery in a store. Other than that, as soon as you produce it, it is discharged, finish. All the load is gone. So, as I said, for this electric charge to flow, you need to have a load, something like an electric bulb, something like, for example, a resistor, something like a motor, something like a transformer. So you need to have a load so that you're going to make a link between the positive and the negative poles. So this is the meaning of battery that was first introduced by an Italian scientist called Alessandro Volta in 1800. And in the honor of his name, now we have got the word volt, which is the electric potential. Therefore, the main components of a battery are the positive pole or electrode, the negative pole or electrode, and the electrolyte that comes in between and creates current. These batteries have got different forms. These days we have got rechargeable batteries, non-rechargeable batteries, we have got the alkaline batteries, we have got dry type batteries, we have got acid batteries, we have got electrochemical batteries, chemical batteries, many different forms of batteries. We have got car batteries, we have got motorcycle batteries, we have got different types, therefore different electrolytes, therefore different charging and discharging at different volts. 6-volt battery, 3 volts battery, 9 volts battery, 12 volt battery, 24 volt battery. So combination to a battery is a battery charger. If you don't have a battery charger, in that case, after a while, that load will totally use up the electric energy inside the battery and the battery is gone. However, some of the batteries are chargeable, some of the batteries are not chargeable. So as you can see in here, we have got different types of batteries available in the market that you can use. Even for fun, just I advise you do it in your kitchen next time. You just take one lemon, pick one, or just a number of them, put them in series, and push a number of nails in them, and just connect them together by means of wire, and put an electric bulb, a small one. You can light it up by lemons, depending on how many lemons you have got and how sour they got, because it all depends on the acid inside the lemons that can work like electrolyte for you. Therefore, as I said, in order for you to be able to make an electric current, you need to have the positive and the negative poles, and at the same time you need to have a load and wire in between so that you can have a current of electrons and protons. That wire can be copper, it can be aluminium, or it can be anything else. I have already explained this to you, so you understand the meaning of voltage. You understand when we say 20 volts, 10 volts, what's the meaning of that? You understand the meaning of force or pressure or potential. You understand the role of the valve to control the flow of current. This valve, again, is similar to that resistor, but the resistor is not just the valve, but also it has to do with the diameter of the pipe, or in electricity, it has to do with the size of the conductor. So we have got voltage, we have got current, we have got the flow. Also, I talked to you regarding the height, I talked to you regarding the diameter of the pipe, which is a means of controlling the flow. It can be the flow of water, or it can be the flow of electrons. Therefore, in electricity, we measure that potential of force or pressure or whatever by means of volts. We measure the flow of electrons by means of amperes, again in the honor of the name of another scientist. Interesting thing is that a lot of them are German ones, like this Mr. Ohms, okay? And again, the electric resistance is measured in ohms. So resistance is a feature that slows down the flow of electrons, and resistance causes an opposition to the flow of electricity. Who in this class knows the equation or the formula for resistance, electric resistance? If someone asks you, hey, could you give me some very, very simple equation that comes from physics, high school? Ohm's law is one of them. Excellent. So Ohm's law is V equals Ri. Okay. So it shows that this R and I and V are connected like this. Okay. Ohm's law. If someone asks you this, just focus on this R. What is the equation for this R? This R is depending, it depends on what? Forget about V and I, R by itself. When I say the resistance of this wire is 10 ohms, 20 ohms, it depends on what? I have not connected that to any battery. So there is no voltage, there is no current. Okay? So it's not a matter of Ohm's law. I'm not talking about the Hector, material. What do you mean by material? I'm just talking about that wire. Forget about volts and current. It's not been connected to any supply. I'm just talking about that wire. The resistance of that wire depends on, excellent Hector, conductivity, and it is not just conductivity. Conductivity. Okay, temperature is a tuning factor, fine-tuning factor. But what are other things? Do you think that the resistance of a 1 meter wire is the same as the resistance of a 10 meter wire? Do you think? Is that the same? So length, correct. Length is another one. So we have got the wire, the conductor, conductivity, and the length. And do you think the resistance of a thick wire is the same as the resistance of a thin wire? So there must be another thing in between. Excellent, Hector. Cross-sectional area. Okay, so all in all, I can say that you can write it down for yourself if you like, or you can listen to this recording later on or watch it. So it is rho times L divided by A. So this rho is the conductivity. L is the length of that wire, and A is the cross-sectional area. So if it is, for example, this L is in terms of millimeter, this A should be millimeter squared. Okay, and then this will be ohms. Okay, so you understand that R is directly related to L and reversely related to A, and again directly related to rho, which is the conductivity, resistivity. So the higher the resistivity, the higher the resistance. The more the length, the more the resistance. The more the sectional area, the less the resistance. This is what we have discussed so far. Now, we say that the effect of resistance is heat, is the loss of the thermal energy. So sometimes this heat is good. We intentionally make this heat. Sometimes this heat is bad. Who in this class can tell me one example of having heat as a good thing? So who can give me an example when I intentionally increase the resistance so that I'm getting heat? Yes, like oven, like heater in industry. Can you give me an example in industry? From mine, for example? What is the thing we have got? Of course, it's not a simple electrical heater or something. Water heater is correct. And have you ever heard of electric furnaces? Okay, we have got electric furnaces where you have got big rocks, big rocks. Okay, so you would like to heat them up. You would like to melt them. Okay, so rather than having a big fire, for example, out of burning something, you can use electric energy to make that big heat so that you can melt down something. All right, but sometimes it is bad. Like, for example, if you have got a motor and if it is heated up, you've got a transformer, it is heated up. You've got a generator, it is heated up. That's bad. That can kill the equipment. So sometimes this heat as a result of high resistance is good. Sometimes it is bad. Now that you have understood the meaning of the current and voltage, I'm telling you that in very general terms, they have got AC currents and DC currents. Direct current or alternating current. So again, I remind you of that positive and negative. If the location of that positive and negative is the same, constant. So at all the time, for example, you can say that where I'm standing, at all the time on my left I've got the positive and on my right I've got the negative. So at all the time the direction of the current is the same from your right to your left. That is DC. But sometimes intentionally we make it in a way in our generators so that the locations of this positive and negative is just changing regularly. In that case, that's an alternating current or AC. The reason why they are doing that, it is not a subject of this presentation in here because it will ask me actually to go into the very detail of generators or something, but it's just telling you that there are very good reasons behind that. We can get a lot of more power out of AC circuits rather than DC circuits, but at the same time, we can get a lot of good controls over this DC circuit. So all I'm saying is that both are available. LV, MV, and HV. They are all available within the market. Okay, so we can get very high voltage DC, low voltage DC, medium voltage DC, high voltage AC, low voltage AC, medium voltage AC. They are both available. Okay, so it's very simple for DC, as you can see in here. So it's not a matter of time, okay? So if this is the time, for example, XS, it's not a matter of time. And all the time, you are having a constant voltage. However, when it goes into AC, you can see that those positive and negative charges are just changing the location regularly, repeatedly. That repetition, as you can see in here, who can tell me this? According to your understanding, what is the name of this repetitions? So it is just this wave shape is repeating itself. What is the name of these repetitions? And Paul, you are fantastic, mate. Okay, so the name is frequency. Okay, Hector, excellent. So do you agree that these repetitions can be repeated in a period of time? Okay, so in a set period of time, I can have these many repetitions, or within the same period of time, I can have these many repetitions. So the top one is what we call the low frequency. The bottom part is what we call the high frequency. But this time period is what we call the period. So as you can see in here, T and F, or period, and F frequency are reversed. So in other words, I can say T equals 1 divided by F or F equals 1 divided by T. Another question for the class is this. If someone asks you in the UK, when you say one period, one cycle, that one cycle means how much second or millisecond? Do you have an answer to that? Do you know how much is it? Do you know how to calculate that in the UK? If someone asks you one cycle, excellent. One cycle means 1 divided by 50. Okay, 1 divided by 50. 1 divided by 50 means how much? 1 divided by 50 means how much second? I'm talking about T. I'm not talking about F. I'm talking about T. So one cycle, which is one period T, is 1 divided by 50, okay, or 2 divided by 100. Or it is 0.02 seconds, not 0.2, 0.02 seconds. Okay, 0.02 seconds. You tell me how much millisecond is that? 0.02 second is how much millisecond. So you have to multiply by 1,000. Okay, excellent. So 20 milliseconds, okay, is what we have got. So 1 divided by 50, my dear friends, yes, is this. Is that correct or not? Is this it or not? First of all, I'm telling you this is second. One cycle is this much second. Is this correct or not? 1 divided by 50. Does that make 0.02 or not? Yes? So it is not 0.2, it is not 2. Now this is second, or when you multiply by 1,000, you get 20 milliseconds. So this is what you have got in the UK. Could you tell me how much is one cycle in the United States? Who knows that? Okay, could you simplify, Maria? 1 divided by 60 means how much? How much second, how much millisecond it is in the United States? 20 milliseconds for the UK, and come on, 1 divided by 60 is 10 milliseconds. Have you got a calculator? Aha, Hector, correct. That's it. So that's second. All right. Hector, is that correct to say 16 milliseconds or not? Is that correct to say that 0.016 that you are saying is excellent? 16.67 millisecond is the correct answer. Excellent. So all I'm saying is let's say the similarities between this frequency and the period. So they are saying the same thing. This is high frequency, or HF. This is LF, low frequency. Okay, so what happens is that from this end, I can say that when you talk about this three-phase, when you think about this AC circuits, okay, it can be divided into single phase and three phase. Okay, who in this class can tell me what is the benefit of a three-phase system as opposed to single phase? Who can tell me that? You have got, for example, not more voltage, Paul. It's not a matter of voltage. You have got air conditioning system in your home. It can be single phase. It can be three phase. At all the time, you just connected that to 220 volts. So it's not a matter of voltage. Okay? It's not a matter of voltage. Alec, you are close, but it's not a matter of... Okay, so the load... It's not a benefit. More load is not benefit. The thing that supplies the load is more important. So in other words, more power. So 3 times more power you get out of that. So all I'm saying is that as long as your load in home, okay, is something like lights or refrigerator or TV or, I don't know, your personal computer or something like that, it's not a big load. So you can handle that with a single phase power. However, if you have got big, for example, powerful air conditioning system in your home, in that case the single phase system would not be sufficient. So you need to have a three-phase system actually to come in between. So again, we have got three-phase system as opposed to single phase. So again, the way how it will be single phase or three phase, it goes back to the design of your generator. It all goes back to the split of the loads. So normally the power company gives you three phase. What you can see in your street, what you can see in your alley, what you can see in your neighborhood, it is all three phase, three phase, three phase. However, you can see that how they have given your home that power, they have just given you one wire, and that is your one, that is just single phase, because you are a residential load, you are not an industrial load, you are not a shopping complex, you are not I don't know, a cinema, you are not an office, you are not a factory, you're just a home. So single phase is enough. So they give you phase A, they give your neighbor phase B, they give another neighbor of yours phase C, and again A, B, C, and again A, B, C. So this is how they will distribute the three phases in your street, in your alley. However, the important thing about this three-phase system is that you have to distribute that as much as you can equally. If you don't distribute that equally, what will happen is that you will have an unbalanced system. And when you have got an unbalanced system, in that case, that's going to be very bad, because you have got unwanted or leakage currents. You will have the overheat of the machines. You will have damage to your, let's say, household appliances or something, okay? So when we are dealing with three-phase and single-phase, we have to be very, very careful about that. So when you think about the electric power, basically this electric power is a multiplication of V and I, basically, together, okay? So this is the, let's say, the way it works. All right. So as you can see, the electric power is basically measured in watts. So this is basically what we discussed. So it's a multiplication of V and I together. And what happens is that this electric power, and yes, so it has got two basically components, two important components. One of them is the real power and another one is the reactive power. So one of them is P and another one is Q. Together, this P and Q make together S. Okay, so as you can see in here, we have got the triangle of power. This S is the apparent power, P is the real power, and Q is the reactive power. Now, I've got a very simple question for the class, and the question is this. When you pay for your power bill, okay, in that case, is it based on P, or is it based on Q, or is it based on S? You tell me. Are you paying for P, or Q, or S? Just as a matter of curiosity. See, you don't have the same idea. All right. So I asked this question in another way. The transformer, right? Let's assume you have got a zone substation, and in that zone substation, you have got a transformer. That transformer is feeding power into your home. In your opinion, that transformer, the nameplate of that transformer, is that in terms of S or P or Q? The rating of the transformer is S or P or Q? Okay, I give you one hint. That rating of the transformer is normally given as MVA or KVA. The rating of the transformer is normally MVA or KVA, and that MVA and KVA, for your information, is the unit of measurement for S. Therefore, the power company has already paid for S. In other words, that power company has already paid for both P and Q. However, when they give that power to your home, you are paying for P, and that W energy is based on P. So what's the benefit of Q? The benefit of Q is that it is working like a facilitator. It is working like a catalyst. It is working like a motorway, a freeway, a highway that you have got. You need to have a pathway for those electrons and protons to move around. Now, if you have a look at that triangle, you can see that there is an angle between P and S. Do you see that? That angle is the angle of, are you on, can you see the triangle or not? As far as I can see, you are on page 32. You cannot see that? You should be able to see that. Is that correct to say that the thing that you are seeing is just P and Q? Is that correct to see that you are seeing? Okay, so what about this page? Oh, okay, now I understand, sorry. Can you see the triangle? Can you see the triangle now? Yes. So can you see the angle between the P and S? Can you see the angle between the P and S? Okay, so that angle is the angle phi, okay? Cosine of that phi is the power factor. Now you understand the meaning of power factor. So when I say, okay, so put it this way, what is the meaning of having everyone, first of all, everyone agrees that normally in the business we would like to have high power factor, is that correct? For example, we would like to have 90% power factor, 95% power factor, okay? If you have got pen and paper, please write it down. Write down power factor equals P divided by S. P divided by S, according to what you can see in the triangle, because power factor is cosine that angle, cosine phi. Now, could you tell me what is the meaning of a high power factor? Why do you want it to be high? Why do you want to have a high power factor? No. That's not because of balanced load. Do you agree that if power factor is 1, 100% unity, do you agree P equals S? Is that right? If power factor is 100% or 1 or unity, do you agree P equals S? Is that right? Excellent, Jeremy, excellent. It means that the utility is telling you that I gave you S. I gave you the whole thing. If your power factor is 100%, it means that you have converted all that S into P. So you have used the maximum power, and at the same time you paid me for that maximum power, because your bill is based on P. However, if your power factor is low, it means that your Q consumption is very high, while you are not paying to the power company for that Q. In that case, the power company will tell you, hey, you know, mate, what's the matter here? The thing is that you are wasting my energy. I have already paid a lot of money for this transformer. I am giving you S, which is a combination of P and Q. You are wasting my Q. You are wasting the highway. This highway is for 1,000 cars. However, you have put only 100 cars in this highway. You are wasting my investment. If I knew from the beginning that you're going to drive only 100 cars, I would never ever build such a big highway in here. You have wasted my investment. That's why you will have to pay fine to the power company for having a low power factor. And who in this class knows in what way you can correct your power factor for the power company so that you are not punished, you are not charged, you are not receiving any fine? Who can say a very, very common way that we use in industry? What is the thing that we, yes, Hector, capacitors. We have got cap banks, we have got capacitors to be connected to our loads. And you can write down for yourself that when we have got capacitors in place, what happens is that they will inject Q to the system, so that the power company is giving you P and Q. You are using P and you are using Q. At the same time, you have got capacitors connected to your load. And again, they will not inject P. P is gone. P, you have used it. But they will inject Q. So they will make a balance so that the power company is happy. It's more like I give you 10 pounds and plus $5. You use the 10 pounds and you will return the $5 to me. That's the deal. If you do not return that $5 to me, I will charge you. The pound has gone, okay? Pound sterling is gone. You have used it, you have spent it, okay? I'm not dealing with that because you will receive a bill for that. But I will just bill you just in terms of pounds, not dollars. So you have to return the dollar, whatever, because that was a package from the beginning. Can I say that in this class, everyone understands the meaning of power factor, the benefits of high power factor, why the power company charges and fines and whatever if your power factor is low, and why you need to have capacitor banks in your site to compensate and correct the power factor and Q. Are you happy with my explanation here? You understand the meaning of power factor, you understand the meaning of the triangle of power, you understand the relationship between S and P and Q. Because this is the end of presentation number 1, and the rest of the pages I'm pretty sure you can read for yourself, and I don't find you can find any problems with that. However, by all means, if you have got any issues, just send a request to the course coordinator and I'll be at your service, okay?